Hi, it's Terry Denery of the MathWorks. So in this video, we're going to talk about how you get your mechanical model, how you build this mechanical model, right? And just to remind you, this is what we're working with, a 4-bar linkage, all right? And we saw that we have a very good Simulink model that we're doing a lot of things to kind of bring mechanics, electronics, and controls together. Ultimately, what I almost call the definition of mechatronics. So anyways, MathWorks is a pretty good company, but doesn't do everything. And therefore, we got a really good partner, very rich partner program. I think there's probably over 1,000 companies that create products that partner with MATLAB and Simulink to do really, amazing things. So we're going to use this one called SimWise 4D. So let me bring SimWise 4D up for you, all right? And I'll just show that, it's a mechanical simulation tool too, but certainly does not have the ability to place controls, much less a PMSM motor with field-oriented control generating the torques that will make it move the way we need it to. All right, but it's an amazing tool for defining the geometry and material properties and interfacing with CAD tools and all kinds of things. So, anyways, from this tool we can bring this all into MATLAB. Right, and so we go to MATLAB and I'll go to my sandbox where this exists and I'll just bring it in. So this command right here, get geometry. Okay, and this one you'll see kind of comes in, recognizes that there's a motor and it's through this motor it's looking for a torque. And by sending nothing in, hit run, we'll see that essentially we'll assume 0 torque. So let's view that from here, and that basically think of this as two inverted pendulums, ultimately unstable by gravitational torques that get generated as it, again, begins to shift. Now, all that's ultimately driven by numerical error in the calculation, but, numerical error is representative of unknowns that will always take place with real systems. So anyways, very useful that we get a model as quickly as that. And I want to just kind of show how we get it. And there's the new model. I double click on it, we'll see it auto-generate all of this, and you might do a little bit of cleanup to kind of make it look nice, but it's pretty close to what we've already looked at, and that it's made up of all these different rectangular extrusions. All right, so let's get into SimWise and let's create a new one. And so there are a number of ways you could do this, and I do have other videos out there where I get into, CAD import through pretty much every important CAD tool there is, whether it's Siemens NX or Solid Edge or Autodesk Inventor or Pro Engineer or SolidWorks or CATIA. They're all available. And if you have some kind of new CAD tool, well, generally you're going to satisfy what we need by being able to export to like step files or ASIS or, what's another one I like? Well, anyways, there's lots of options there. All right. So anyways, let's kind of get into this. And so we're creating a 4-bar linkage. So we basically need to create our links. All right. And so I'll begin by just creating a rectangular extrusion. Let's set its geometry. I'm going to make it 0.01 in the X dimension, 0.02 in the Y, and then let's make Z 0.1. Apply. Now it's very convenient to say mechanical simulation tool too. So I hit run and I always can kind of update myself with where am I with regard to this. All right, and so I'd say the next step is let's just place it where we want it to be. And I think it's always kind of nice to put things at origins. It often makes sure measurements come out very clean. So let's go ahead and move this at 0, 0, 0. And then with regard to Z, I know it's 0.1 meters high, and so I'm gonna, and that's essentially the center of mass, so let's make it 0.05. Does that do it? Yes, it does. All right. So all we did was move it, but it still falls freely due to gravity. And so now we want to begin to really kind of put the linkage together, which means that we're going to define some of our connections. All right, and so let's zoom in a bit with this. All right, and the connections are defined by precise placements, but the placements need to generally dictate some orientation. And so a critical tool in working with mechanics is well, I call it a Cartesian coordinate system. But it's essentially, a representation of location as well as orientation. And you'll see that little XYZ coordinate system showing up on that surface as I placed it. And notice it's a little bit out of rotation with my global ones, which is the black ones. And that difference is actually expressed quite well by these Euler angles. So a rotation of minus 90 to 90 on X and Y and these things called Euler angles will set that orientation relative to our global coordinate system. Anyways, topic we may get into a little bit more deeply as we go through this, but let's just kind of do some things here. Let's place it in the center of the part, but let's make it on the far end and make it minus 0.05. Right. Okay, so that locates it. Again, hit run, see where you stand. Right, so that happened pretty quickly. So I'm going to just do the motion frame by frame. But the point I want to make here is that that frame is attached to this body. All right. And let's see, another thing I want to do is I want to go into appearance. I think I'll keep it gray, but let's give it a good name, and I'm going to just call it A. And my parts are going to be called A, B, and C. All right. Now let's reset, and now let's create our first joint. All right. And so joints are really about position, but they're also about orientation. And so I'm going to kind of quickly do this first one. I'm going to create what they call a revolute joint. All right. And you can see that the shape of this joint is cylindrical. That's just a helpful image. And it means that it's allowing rotation about the axis of that green cylinder. All right. And again, it's very, very ideal, but it's kind of a perfect, balance based on the location of the revolute joint as well as the placement or balance, being at the center of the part. So anyways, I'm going to throw a little applied force on there and that'll rotate it. That's a really big applied force. So maybe I'll go in here and, well, it's really big for something as small as this is. So let's make it minus 0.00001, right? And that should be enough, right? Because gravity does act, and all we got to do is get it moving a little bit, and all of a sudden we have the rotation. All right. But we're doing pretty good here. I'm going to delete that whole motor thing. All right. And I'll call this GA, ground to A. All right. And now let's create our next one. And so I'm going to just go Control C, V, paste it. And I'm going to create this one. And I'll call it B. And B is going to have a bit of a different size, but we'll have the same cross section. And that's the advantage of keeping it or copying it from the first one. All right. Okay. Now, this one is kind of rotated. And again, my familiarity with the geometry, the definition of it, I know that I simply need to rotate about its axis that way to get it horizontal. And so now let's make our connection between these two. So the connection between B and A. All right. And so again, we'll get our chord frame tool. We'll place a chord right there. Place one right there. All right. And I like good user interface, and there's a lot I like about this tool with regard to user interface. And one of it is that I can do the same thing to two of these frames at the same time. And so I'm just locally positioning them along their X and their Y axes. Now, the trick now is to kind of get, well, it's not really a trick, but individually now I need to make the assignment on the location in the Z direction, and that places it that way. Again, notice this is a local assignment, and we see that right here as it tells you it's in terms of the B coordinates. And the B coordinates for the body, notice X, Y, Z. All right. right? And so now we just need to join these two things, right? And we go here, and a lot of defaults are really working for us. And I think you'll kind of notice that it's kind of nice that it shows the axis of rotation very correctly for us. And I'll just say that a lot of that stuff just kind of again happens because there's good user interface. All right. And there are definitely some videos of me doing, mechanical model building out there where you can kind of see the intricacies of how you do this. But the point here is that you can do this stuff very quickly, and as soon as you kind of teach yourself to be proficient with these, I think you'll find the same success. All right, so let's create our last link, and so this one I'll go Control CV, and this time I will call it C. All right, and now I'll make a little bit of an adjustment on the length. Let's see, 0.25, apply. And let's move it out of the way. I like that there is kind of this way to interface with these things visually too. It's always a little tricky in 3 dimensions, but let's go ahead and now place kind of our final coordinate frames in here. And so I'm going to place one there, and I'll place one here, and I place one right there. All right, and so this time I'll do the official or the property assignments for X and Y for 3 of them at the same time. So 0, 0, right? And now let's just go get each one of them to kind of finish it up. Okay, and that places it at the end right there. Oops, that's 2.5, so that's, there you go. It's half the length, basically. And so on this side, it's minus 125. That places it on the end, it's here, it's minus 0.1. All right, and I think it's a good idea. Let's reorient this back to vertical. All right, and now let's take that frame and that frame and do the connection. Okay, and let's look at it straight up from the x-axis, and we'll hit run again, just kind of seeing where we stand, and we see those first 2 connections have been made. All right, and this one I'll call B to C. All right, and we're almost done at this point. And so what I'm going to do is take that last frame, and with only it selected, I'll click on this, I'll create another joint, and you'll see it kind of gives you this information of how things are going to be done. And if only one frame selected, and that's the one right there, well, it knows what body it's on, and it's going to say, oh, okay, you just got one selected. Let's create a new one for you, and we're going to place it on the background. And I hit create, and I hit run, and everything works pretty well. Well, let's do kind of our last thing, which is C to G. Okay, and let's drive it. And here I want to kind of show it transparently. Right. I want to focus on this one. And so instead of simply being a revolute joint, let's make it a revolute motor. Close. And I might even include that in its name. Motor. Oops. Motor GA. All right. So, and we'll show it shaded again, and we'll hit run, and there's your model. Okay. And with that, let's save it to a new name. And this one I'll be really creative, and I'll call it small 4-bar 2. All right. And with that, let's just kind of prove that it comes into Simulink nice and cleanly with this name of small 4-bar 2. Okay. And I'll hit run. And we'll view it from this orientation. And I think eventually it tips over just like our other one. Notice it is called small 4-bar 2. And I think I'll wrap up with one last thing. All right. And this is that that motor can be interpreted multiple ways. And there's a very useful way of saying, well, instead of receiving torque, let's just allow you to define motion. All right. And we'll see that this is done in our original model. All right. Oops, messed up. So let's get there. Let's get here. And it's right here. All right. And so this is a smooth step position. Here that we sent it from 0 to 90 degrees. And I want to just copy that. And we will paste that in. Actually, I think that's good. So let's just send it in. Probably do a little bit better cleanup than what I have right now. Let's just hit the space bar. Let's hit run. Okay. All right. So anyways, we're going to take this as our starting point as we move into choosing an electric motor. And that choice will really be dictated by the motion that we just sent into, which then ultimately determines the torques required to do it, right? And we'll see, this is how we're going to know both torque and speed. So thank you.